Hello, my lovely chemists. Um, Low-key, I did already film all of this, and then it somehow deleted itself, and I did have a near mythic crash out about it, but it's so chill, and I'm so happy to be teaching you about covalent bonds, so we're gonna do our best. Um, Hopefully yesterday was helpful visuals and kind of gave you a bit of an introduction, but I'm hoping today will serve to get us kind of all better on the same page about what the heck this means. And primarily, our big skill is how to draw and represent this type of bond. So let's get into it. So, as we know, this is page 61 in your notebooks, which I hope you already have out. But we know that all of our atoms want to be stable, right? They want to be stable. And when we say stable, that means they want to have a fall, valence shell. Right? So that outside ring in our Bohr model, our most exterior electrons, those are the ones we're going to be focusing on. Those are the ones that matter. And having a full shell of those makes atoms happy and fulfilled. So, usually this is called the octet rule because, as we know, on those bigger rings, it can fit up to 8 electrons, right? So when we say that they want to be stable, we can think of it as they want to have 8 electrons in that outside ring. Okay, awesome. We're gonna see, so the whole point of being stable is full outside shell, right? And any type of bonding that we've talked about and are going to continue to talk about involves only the valence electrons, right? So when we talk about most of chemistry, all this bonding stuff, all the reaction stuff we're going to get to later, it's all about electrons. The nucleus is there, it's important, but the electrons are the ones actually interacting with the surroundings and with each other. If I have two atoms and they're gonna bump into each other and have some kind of interaction, the part that's gonna actually touch is the outside, right? The valence electrons. So for all we're gonna do today, we're really just gonna focus on the valence electrons. We're not gonna really draw full Bohr models for a while. We're gonna just focus on our valence. And remember, there's a super easy way of getting your valence. We just look at the numbers at the tops. So make sure you're using this and practicing that, getting help from your neighbors if you ever forget. Cool, so they want to be stable, and we've learned there's 2 ways of doing that so far, right? We talked about ionic bonding, when they lose or gain electrons. We've talked about metallic bonding, where there's this weird soup of electrons. And then finally, our last type, and arguably the one that we're going to spend the most time on, is covalent bonds. So we've already done metal, non-metal, that's ionic, metals are metallic, and this one is what if I have non-metals sticking together? What do those do? So, non-metal atoms, when they interact, they're going to actually share their electrons. So hopefully you kind of started to see that yesterday, but let's make sure we're all super clear on that. So we're going to talk about this type of bonding. It's about sharing electrons. Let's get into it. So any kind of non-metal, of course that bond's going to act differently, and we're going to talk about it differently. And so that's why it's super important that before we approach any problem, we kind of check in and be like, okay, hey, it's non-metals. This is covalent. That means I'm allowed to do the following. And really the big skill we actually want from this section is how to make something called a Lewis dot structure. So this is the main thing, how to make a Lewis dot structure that we're going to start talking about today. So that is the drawings we make, the type of model we make to show sharing electrons, to show covalent bonds. So we're going to start that today. We're going to be practicing it for a while. So, do your best to follow along. I want to do this little overview to start before we jump into making our own. I want to kind of talk you through what these look like and what you might see in a Lewis structure. And then we'll practice trying to make one of our own. So there's kind of 2 things that electrons can do when a bond is happening. Sorry, when in a covalent molecule, just in general, there's kind of 2 options for those electrons. They can be unshared. And we call that a lone pair. So if we see dots in these structures, if I see this, those dots are unshared. So they only belong to X. They don't belong to any other atoms that are around. They're unshared. Notice this is called a lone pair, right? Pair. So like if I had a pair of socks, I have one pair of socks. There are two socks in the pair, right? So we're gonna always see these dots as pairs. There's always gonna be two at a time. That's just a general guideline. We want to draw them with a partner, two at a time. So, if I don't need to share, I'm going to keep my electrons all to myself, but a lot of the time we're going to want to share, again, for the goal of becoming stable. And that is what we mean by when we say a covalent bond, that is shared electrons. So when we look at these structures and we see a line, that means that we're trying to show that those are shared electrons. So like this. Two atoms with a line in between. That line is shared electrons. And it's shared by both partners. So like this X has those two electrons, and this X has those two electrons. They're sharing them. So they both get access to the two electrons. So anytime you see a line, it means two electrons. So like let's see an example and see if we can kind of dissect what's going on with our electrons in this example. So I have two H's here. So H2, and I have an O. So H2O. This is what water kind of looks like. And let's kind of look at what's going on here. I notice there's some dots on oxygen. So again, when you see dots, that means unshared electrons. There's two lone pairs attached to oxygen. Okay? Two lone pairs, two pairs, which is the same thing as 4 electrons. 4 unshared electrons. Cool. And then we kind of look at what else is attached to our oxygen here. So there's the dots on it, the lone pairs, and then there's also some lines attached to it. So it also has these lines. Those are bonds. It has 2 covalent bonds. Awesome. Maybe. Cool. Yep, okay, there we go. 2 covalent bonds. And remember, when we see a line in these structures, that is representing shared electrons. So 2 lines are representing 4 shared valence electrons. Okay. So let's kind of summarize that. I want to look at oxygen, and I want to practice that we can tell how many electrons oxygen has based on one of these structures. So what you're going to want to do when we assess this, you're going to want to look at anything attached to the atom. So like what's attached to oxygen? I see we have these dots, right? So there's 1 electron, 2 electrons, 3 electrons, and 4 electrons. All right. And there's a line. And remember, again, you can kind of draw it like this if you prefer. The line is representing 2 electrons. So my 5th and my 6th electron attached to oxygen. And then over here, another line, my 7th and my 8th. So you're looking at your atom, and then you're looking at anything attached to it. And that's how many electrons it has, how many valence electrons it has. So from counting it out, oxygen has 8. And that's what it wants. Oxygen's happy with the situation right now. It's good with this bonding pattern with 2 single bonds. So that's what we're going to do a lot with these structures once we start actually making them, is we're going to constantly be checking if our atoms are happy or not. Do they have 8, or do they need to like bond more, or do they need to bond less? Like, where should my electrons actually go in the picture? Again, just an overview of what we might see here. Sometimes we'll see just one line at a time, and that is called a single bond. So just one line. And as we talked about, one line means that there's 2 shared electrons. 1, 2. So both of my H's have access to those 2 electrons. Now, this is one of our big exceptions. We just said they want 8 electrons, but right here, this hydrogen only has 2, right? It only has the 2 that are shared in that bond. Is that fine or not? Chat with the neighbor. Why is 2 electrons good for hydrogen? Maybe pause for a sec. And the reasoning on that, I'm going to draw my little Bohr models over here with my electrons. Okay, so hydrogen, with its only has 1 proton, it only has 1 electron. So if I was doing my Bohr model, and I start on that first ring, hydrogen only has that first ring, right? So if I like rearrange this a little bit to kind of show that they're sharing here, let's see. Got a circle with my 1 electron, and maybe they get close enough to one another that this one can bring its electron to the table. But let's kind of see how they're like in the middle of both. They're being shared. That's okay, because if that first ring, that only ring hydrogen has 2 electrons, the first ring only fits 2 electrons. So that's why hydrogen is one of our main exceptions here. The first shell, if you want. The small shell. So every single time you have a hydrogen, it's always just going to have 2 electrons. Only 1 single bond. You would never ever give it dots or anything. You would just have 1 line anytime you have a hydrogen. So that's a little trick. The more you do these, the more you'll see patterns and stuff, which is very helpful for you getting efficient at this. Okay, so single bond, 2 electrons, 1 line. Over here, you'll never guess. When there's 2 lines, it's called a double bond. Whoa. And so each line in the structure is 2 electrons, so 2 lines is going to be 4 shared electrons. All right. What if we had a 3rd line? That's called a triple bond. And each line is 2 electrons. So if I have 3 of them, that's going to add up to 6 shared electrons. So again, let's kind of practice here, evaluating whether or not my structure is good, whether or not my partners are actually stable and happy from this bonding. So the way you do that, again, you look for anything attached to each atom. So this is going to be something we do constantly. We're going to look from each thing's perspective, like from this nitrogen's perspective, what's attached. From this nitrogen's perspective, what's attached. So like, let's practice that. From this nitrogen, I have a dot here, right? And a dot here. That's 2 electrons. And then I have a line, which is 3, 4 electrons. Another line, which is 5, 6. And then 7, 8. It has an octet. It has 8 valence electrons. That's something you're going to do over and over again. And it's only a good structure if everyone has that going on. Like, if we look from this side, the other nitrogen also has 8 attached to it. So it's happy. Everyone's happy. This is our structures. If you're curious about like why this is being held together, and the whole point is stability, but like the force holding it together, we got these negative shared electrons hanging out in the middle. I guess I'll be explicit. Wait. Fraction material, sorry. Double checking what the sentence is. Shared electrons. And then, so we got these negative electrons in the middle, and then we have these two nuclei, these positive protons, and they're kind of like attracted to those shared electrons. They want to hang out there because they want to stay with those electrons and maintain that full shell. Cool. So hopefully you already have PS 4.2 in front of you. For whatever reason, I insist on teaching this differently than some of my colleagues do. So the rest of our notes on this are actually going to be in 4.2. I'm going to make a little note so we remember. So if you don't already, make sure that PS 4.2 is in front of you, and that way when you're looking back on these notes later, you can be like, where is the instructions? And we have to actually look at that separate packet. So let's make sure we keep that on us, and let's move on. So this page is kind of like an overview, right? Just kind of talking about like what this might look like. Now I want us to practice making these structures. These Lewis dot structures, Lewis diagrams. So those of you who practiced yesterday and used the simulations, like the ones I've seen so far look good. So if you liked that strategy, then there you go. If you want to like draw the circles with the shared dots, like if that is working for you, you can totally use that. I'm going to show you 2 more ways of doing it, just to give you some variety and some options of whatever like is clicking for your brain more. So we're going to do 2 examples together, and then when you do your own practice, maybe try both and see which one is kind of feeling better for you. They're very similar, but just one's a like slightly more visual way of doing it. So yeah, let's talk on through this. So you can see we have like 2 different strategies step by step, so you can easily look back at this and follow the steps one at a time if you ever are trying to do one of these examples. Okay, let's try this side first. So I'm going to follow my steps. First thing, I have to see how many valence electrons there are. Right? Sorry, it was being really echoey, which might just be how it is, and it was throwing me off. Okay, anyway, so let's do that. Again, you can get your valence electrons from the periodic table, which is right here. Remember, valence electrons are the numbers at the top of each column next to the letter A. So you follow along with me if you want, but here's our example. I'm going to have a carbon and a nitrogen and a chlorine. So the carbon has 4 valence, the nitrogen has 5, and the chlorine has 7. So that is, oh my god, it's too late. It's 16, yeah, embarrassing. That's 16 total valence electrons that are going to be available in our structure. So some of them might be shared, some of them might be unshared, and it's kind of up to us to figure that stuff out. Okay, so always do that first. We want to know how many electrons there are, so we don't accidentally create or destroy matter and break all these intergalactic laws or whatever. All right, so I want to first kind of just get the setup of my molecule, like look at what atoms I have, and just kind of put them in place. And there's some guidelines for this. Like it says here, we're going to place the first element in the middle. Unless it's hydrogen, because we know hydrogen can't really make very many bonds, so hydrogen's always on the side. But in general, that's the trick for it. But the first thing in your structure, the first thing in the formula first. So I'll put the C in the middle. And then you put everything else on the sides. And the more you do this, the better you'll get at it, but we're going to usually be pretty symmetrical. So I put my C, my first thing in the middle, and I'll put my other stuff, my N, and my Cl on the sides. And then we want to make this a molecule, right? We want to make them connected to each other, sharing. So I'm going to connect them with single bonds like my instructions say. Like that. Cool. So, how many electrons have I showed so far? I have to keep track of my electrons, right? So, I wrote a line and I did another line. Each line is 2 valence electrons, right? So, with 2 lines shown so far, I've shown 4 so far, which means there are 12 more valence electrons that I haven't shown yet that I have to put somewhere in this structure. Okay. I've made these notes so that I want you to be able to look back and be like, oh, I did this, and then I tried this. And like you can kind of see the steps instead of just the end product. So let's go down to step 4. I'm just going to rewrite what we already have. And then let's add what it tells us to add in step 4. Add the remaining valence electrons as lone pairs. That's my suggestion. Just put dots first, and then we might move them around. But let's just try that. So again, I have 12 electrons more. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This bothers me, sorry. Okay, cool. So again, I'm just going to put that down here just so you can kind of see what we would do next. All right. So once you kind of got the basics down of like, I have this many electrons, I have these atoms, now we have to make sure everyone's happy with the situation. So let's kind of practice that. Let's see. This N, again, we look at what's attached to it. So this N has these 6 dots on the side. Cool. Right, 1, 2, 3, 4, 5, 6. And then it has a line. And remember the line is 2. So 7 and 8 represented there. Okay, so nitrogen's pretty happy right now. As far as it's concerned, we're done. But you have to check all of the partners. So now let's look at this carbon. The carbon has a line, 1, 2 electrons, and another line, 3, 4 electrons. That's illegal. Carbon is not happy. It is sad and unfulfilled from this bonding situation. So all that means is that at this point, and it's going to be a lot of trial and error because you guys are just learning and you don't really know the patterns. So all I want you to do is try it out. We're going to move our electrons around. So you have 2 options here. You can form a bond, and a bond is going to cost 2 dots, right? So I could erase 2 dots or move 2 dots and then make a bond. Or I could leave them as dots, leave them as lone pairs, but like maybe I can move the electrons around. So like you can write this with arrows or whatever. We have the whiteboards in class, so I really recommend those because they're easy to write and change. Always do pencil, different colors, something so you can kind of keep track of the changes you make. But I don't know, maybe first you erase some dots and you try just putting them on carbon because you know carbon's not very happy. But now that I did that, now chlorine doesn't have enough. Chlorine only has 6 right now. So that didn't really work. So you kind of just, like, it's trial and error. You try something. So dots didn't work. Maybe I try making a bond eventually. So I'm going to take these dots and I'm going to put them in the middle and I'm going to make a bond. Okay. So I was able to move dots. I was able to move electrons, but my chlorine is still happy. Even after sharing those 2, it still has 8. So that seems like we're kind of on a better path here. There are multiple right answers. That's allowed. But I just want you to try something and see what it does. And then if you don't have the right answer yet, just keep trying things. It's going to take practice. Maybe we try doing the same thing on the other side. I feel like I usually see people doing this. And, okay. For things to be right, you can't forget step 6 and 7, of course. So let's check it out. First rule is everyone has to have stability. So full octets. So let's check that out. If I draw it this way, nitrogen has 1, 2, 3, 4 dots. And then 2 lines. So 4 here, and then another 1, 2, 3, 4 over here. So nitrogen has 8 valence electrons, which is the whole point, right? It's happy. Smiley face not required, but let's have some whimsy up in here. And then from carbon's perspective, it's attached to 4 different lines. Each line is 2 electrons, so 1, 2, 3, 4, 5, 6, 7, 8 also. And then chlorine over here. Again, 2 lines, so 1, 2, 3, 4, and then 4 dots. 1, 2, 3, 4. 8 valence electrons. Yay! Check. And then the other thing, matter can't be created or destroyed. So let's make sure I didn't accidentally lose a dot along the way. Let's make sure there's the same amount of valence electrons that I started with. So we started with 16, right? And then let's check here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. All right. So I obeyed all the rules. This is a valid structure. This is a correct answer. And there are other options that also would work, but as long as it matches these two, I will give you credit for that question. Awesome. So that's one strategy. Let's try another problem. This is pretty similar, but it might be a little bit more visual if you prefer. We're going to still try to show our valence electrons, but instead this time we're going to start by just kind of showing them as dots to start off. So again, first thing, put it in the middle. So I have a carbon, and I have another carbon, and I'll put them in the middle. And then whatever else is in the formula, just kind of put it around. Again, it's usually going to be symmetrical, so like you could try different things, but I'm just going to put it like this. I think that's a good way to start it. And then, like it says, we're going to put dots to represent their valence electrons. So it's kind of like a Bohr model, but we're only looking at the outside. So let me do that. On my periodic table, I know hydrogen has 1. Carbon has 1, 2, 3, 4. Carbon has 1, 2, 3, 4. Hydrogen has 1. So that's the first step. And again, I'm going to kind of show it separately as we go. And like the last time, we have to count how many valence electrons we have. So there's 1 dot, 2 dots, 3 dots, 4 dots, 5 dots, 6, 7, 8, 9, 10. We have 10 total valence electrons available. Really easy to mess up this method if we forget to, like, it's so easy to erase and like forget you erased and then like getting confused with that. So always remember this. You can always come back and double check that you didn't lose any along the way. So again, I'm going to just draw what we had earlier. And kind of what we notice here, like you can put the dots wherever to start off, but I want to connect these. I want to make bonds. So what I can do, I can kind of take my electron that was here, and I'm going to draw it kind of facing the other stuff so that it can create a bond. And then when you have dots facing each other like this, a line is just representing 2 dots, right? So I can kind of connect them like this and show that these are going to be connected. And then again, check if they're happy or not. And if not, we're going to have to change it a little bit. So, take a look at it. Hopefully we notice the hydrogen has 2, so that's happy. But then my carbons, both of them, are not happy. They only have 6 electrons right now, which is not enough. So again, you have 2 options. You can move 2 dots together and make a bond, or you can just move the dots. Those are the 2 options. So it might take some trial and error. Again, I'm just going to write what we have already. That way you can look back at the process. All right, and let's see. I can take, maybe you try things. Eventually, I hope, you kind of realize that both of these carbons need more electrons. And if I just took from one, then that one would have less. But if they both need more, I can kind of put my dots in the middle and allow these guys to bond. And then let's do the little check here. This hydrogen has 2. This carbon, how many valence electrons does that have right now? 2, 4, 6, 8 with the 4 bonds. This one also 2, 4, 6, 8 with the 4 bonds. And then this one only has 1 bond, 2 electrons. That's good for hydrogen. So I'm checking that off. And then I can double check. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons, which is what I started with. That follows the rules. Awesome. So hopefully you can try one of these strategies. Again, follow the step by step. Be patient with yourself. It takes practice. That's the whole point of like learning something new, is that sometimes it's a little challenging, but you totally can handle it. So there's a few examples on the next page. 1, 2, 3 examples. Try them. There's some tips over here. Remember, put the first thing in the middle, unless it's hydrogen, and then put the other stuff just kind of around it. Okay? Might take some practice, but for this class it's going to be pretty symmetrical, so maybe try to arrange them like that. And yeah, pause the video, try them, help your neighbors, try one of the strategies, and then you guys can go over it together, or I'm going to start going over it now. Let's try this one with the dot method. So again, I'm going to put the first thing in the middle, in, and then my other stuff to the sides. And let's put our electrons. Hydrogen has 1. And my nitrogen has 5. 1, 2, 3, 4, 5. And I'm noticing I can arrange my dots so they're kind of facing each other, and I can do some connect the dots for the bonds. Sorry, my bad. I should have, let me back it up. Before I do any connecting, I should probably check how many total I have. Do not skip that step, please. So it's 1, 2, 3, 4, 5, 6, 7, 8. Okay. Then I'll start connecting them. Okay, and I notice this is actually done. These my hydrogens each have 1 bond, 2 valence electrons, and my nitrogen has 3 bonds, 2, 4, 6 electrons, and 2 from the lone pair. So it has 8 total, and everyone's happy. That one's done. Maybe I'll try the counting thing over here. Sorry. My carbon has 4 valence electrons. My oxygen has 6. But I have 2 of these. So again, 16 total. So once I have my total, I'll just put the first thing in the middle, and I'll put the other things on the sides, and I'll just start connecting. So just connecting them, I already have used up 4, so I need to show 12 more. So up to you how you use those. I suggest just do all dots and then move them if you need. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So my carbon's looking kind of sad. So eventually I try to figure out that, hey, if I put those 2 dots here as a bond, put these ones here as a bond, now my oxygen has 8, my carbon has 8, and my oxygen has 8. So that would be my final structure. There's 2, 4, 6, 8, 10, 12, 14, 16 total. So that is the correct structure. So maybe it takes us a while. That's totally fine. I feel like we get mixed up on this one sometimes. I'm going to do the dot thing again in case people like that. So it starts with hydrogen, but hydrogen never has more than 1 bond. I would never put hydrogen in the middle. So instead, I'll put the next thing in the middle. I'll put my oxygen in the middle. And then just from experience, like I said, and you'll get used to this, a lot of our things are like either one thing in the middle and stuff on the sides, or our structures for this class are just like a few things in a row. I know it's usually going to be symmetrical, so let's set it up like this. I feel like that's probably the hardest part about this question. There's never like triangles or anything. Like I feel like every year someone's like, I did this, and then you're like, I'm confused. Why? So it's totally fine to try things, but like there's no way to make this work, right? Like no matter what, your hydrogens end up with multiple bonds, and it just is confusing. So that's another thing. Like if you are totally stuck and you're like, I followed the steps and like I cannot get it to work, try putting them in a different order or something, or like recounting. That's probably what happened. Okay, cool. So I'm going to do the dots. 1 on hydrogen, 6 on the oxygens, 1 plus 6 plus 6 plus 1, get your electron total, and then we can start connecting. And if I do that, that's it for this one, actually. So it looks kind of crazy, but as long as they're in the right arrangement, it's pretty simple to get them. So that way my hydrogens have 2, my oxygens have 8. Everything's good. Alright, so again, up to you which strategy you keep practicing with. There's plenty of practice in this packet, and we're going to be working on this for a bit. Cool. Alright. I want to throw in I want to throw in the naming for covalents into this video because, I don't know, why not have it on hand? Reminder, we spent all this time on talking about ionic stuff, and we learned all these rules for ionics. It's totally different for covalent, right? Like, it's a different thing. It's annoying, but that's how the language of chemistry works. It's pretty complicated. But that's why we have our resources. Like, remember, the packet has the naming tree in it. I recommend you really practice with that. And at the top of it, the very first question you ask yourself is, do I have a metal and a non-metal? And the naming tree kind of leads you to be like, yeah, I do, it's ionic, or no, it's not, and it's covalent. So do that first, make sure you know you're allowed to do the rules here. But yeah, if you do have something covalent, this is where we start using prefixes. You don't have to memorize these. They're on the naming tree, and they're also over here on the right. So it's these things. Or I guess these things. So this is a thing for covalent stuff. For ionic, we knew the charges. So we knew how many partners had to be there and how to make them happy. But here, we don't really know how many of each partner you need because there's no charges. So that's why we say it as part of our name to represent how many of each element you have. So a prefix is like a thing you put at the beginning of a word. So there's rules, of course. Again, it's on your naming chart. For the first element, if there's more than one atom of the first element, use a prefix. And then we're just going to say our element's name. And then for the second thing, so it's just going to be 2 things for us. It's going to be like the first element in the compound, then the second element in the compound. The second element, no matter what, even if there's only one, we're going to always and like with ionic, we're going to change the end to "-ide". Okay. So this one's simpler than covalent. Covalent is simpler than ionic. There's not all the special exceptions for the names, but you do need to know when to do what, right? So that's where that tree comes in mind that I hope you're practicing with. So let's follow this through, huh? Down here, I have nitrogen and oxygen, which are both nonmetals. So I can use my covalent rules right here. If there's more than one atom of the first element. So N is my first element. There's only one. So for the first element, I don't have to use the prefix if there's only one. And then for my second element, it's this O. And I see that this means that there's 2 of the O's. So that means I have to say di at the front of my second word. So I say di, again, because there's 2 of them. And then I say the name of the element. So O is oxygen. But I change the end to "-ide". So the end of "-ide communicates that, hey, I said the couple's name. I wasn't just listing random elements. These 2 are a little unit here. Cool. So you've probably heard these names lots of times and not known that it means it's covalent, but now you do. For example, maybe you've heard of this one. So again, let's try it. First element is C. There's only one of it, and if it's the first element and there's only one, I just say the name, which is carbon. And then I have O as my second element. And no matter what, I have to use a prefix for the second element. So I can look at my chart. For 1, the prefix is mono. And then again, O is oxygen. So ox. I guess technically it's like that. Again, I don't care about spelling. If you put 2 O's, that's fine. Monox, and then change to andide. Carbon monoxide. Maybe some of you have heard of it. Hopefully you have a detector for that in your house. If you don't, make sure you check and make sure whoever is in charge of your household gets you one, because you can buy them at the store and they're very helpful, because this is something that can come out of your stove that is more dangerous for you to breathe in. So something to be aware of. Carbon monoxide. Cool. One more thing. Sorry to throw in another challenge here, but I do want to point this out. NO2. That is not the same thing as NO2 with a charge. Okay? So this, NO2 with the charge, when something has a charge, it's called an ion, right? So this is on that special list we've been talking about. This is a polyatomic ion. So because it has a charge, because it's able to be an ionic bond, it's special. It has that special name. So this is so tricky because it looks so close to this, and it's really hard when you're learning to try to figure out when we're talking about which one. But we're gonna practice with this. I put some practice in the problem set. If it has the charge, if it's ionic, if it's in an ionic compound, if it's an ion, then it has the special names. If there's no charge, then it's just a normal covalent thing, and we do this. So that's pretty tricky, but I want to point it out and have you have it written down for future. Okay, so I think that's where I'm going to cut this off, and please work on these other examples here of naming, help out your neighbors, move on to the other practice in this packet, and we'll keep doing more practice together tomorrow. All right, have a great day, folks. Still recording. Awesome. Now